Before we talk about the algorithm that we can use to solve systems of equations, we want to talk briefly about certain special forms of a matrix. And these are called row echelon forms. So in the last video, we saw a particularly nice row equivalence. This row equivalence was nice because it allowed us to simply read off the solutions to the original linear system. The top row tells us that x is 2, while the bottom row tells us y is 3. In order to solve linear systems, we would like to have an equivalence of this kind for any linear system. This is slightly too much to ask in general, but there is something close. So we say that a matrix is in row echelon form if all non-zero rows are above 0 rows. The first non-zero entry in a non-zero row, this is called the leading entry, is 1, and the leading entry of a row is to the right of the leading entry of any rows above it. We say that a matrix is in reduced row echelon form, which we normally abbreviate as RREF, if the leading entry is the only non-zero entry in its column. It's a wordy definition, but with a couple of examples, it's not hard to internalize. If we look at this matrix, we can see that this is in row echelon form. There are no 0 rows, so the condition that the 0 rows are at the bottom is trivially satisfied. In each row, the leading entry is a 1. The leading entry in row 2, moreover, which is below row 1, is to the right of the leading entry in row 1. However, our matrix is not in reduced row echelon form. The reason for that is in this second column, there is a leading entry and a non-zero entry. Once you're in row echelon form, it's very easy to get into reduced row echelon form by simply using the leading entry to clear the rest of the column. So when we subtract row 1 from row 2, this puts us into reduced row echelon form because we have a 1 as our leading entry here, and it is the only entry in this column. We have a leading entry of 1 here, and it is the only entry in that column. We can still read off all of the solutions to this particular system from the reduced row echelon form. This system has infinitely many solutions. We can solve each of these two equations for x in terms of z in the first case and y in terms of z in the second case. So we get the two equations. X is equal to 1 minus 2 times z, and y is equal to 2 minus z. If we think about this thing as a triple of numbers, then we would write down the solution space as the set, or we could simply substitute these two values in for x and y to write this as a set of triples parametrized by the real number z. We call this usually a parametric solution because our solution is parametrized by some variable z, where we get to make a choice. So let's try another example. This matrix is neither in reduced row echelon form, nor is it in row echelon form. The first problem is this second row. Any row of zeros should always appear at the bottom of our matrix. Also, we have a leading entry in this first row, which is not 1. And worse yet, the leading entry of the first row is to the right of the lower leading entry in the third row. If we rearrange, next, we need to make sure that in this second row, the leading entry is a 1. We can do that by scaling the second row by 1/2. Now, we have put our matrix into row echelon form. The leading entries fall on a diagonal, starting from the first column to the second, and our leading entries are in fact all 1s. The only thing standing between row echelon and reduced row echelon form is this 2 in this column. If we take twice this second row and subtract it from the first row, then we'll be done. And just like in the last example, our reduced row echelon form tells us that we have more than one solution. So this gives us our parametric equations, parametrized by z, and we can express this as a set of triples. In the next video, we'll write down the Gaussian elimination algorithm, and we'll talk about how we can use that algorithm to solve systems.